Hey guys, it is me again, and I am here to talk to you about light and optics. So here's our PowerPoint. What makes light? So light is made when electrons get really excited with energy and move between the orbits of an atom. So remember when we talked about our atoms in periodic table, we talked about how there are different orbits. So when that light is absorbed and emitted, we are then able to see light. Yesterday, you talked about the electromagnetic spectrum, and you should have watched my video or read through the PowerPoint. And the visible light is only a small part of the electromagnetic spectrum. Remember, I talked about Roy G. Biv? That's the only part that you are actually going to be able to see with your eyes. It has a wavelength that's between about 400 to 700 nanometers and is the only kind of electromagnetic radiation that we can detect. So the parts of the spectrum, if you haven't done so yet, you have a foldable that you have to do, and this would be really great information for you to put on that foldable. But here's some information on your radio waves. These waves have different wavelengths from hundreds of meters down to less than a centimeter. This is an FM radio wave, and that is actually, if you didn't know this, the FM wave is shorter than the AM wave. And that's why AM radio stations can be heard for longer distances. And then the longer the wave, the further the signal can travel. And microwaves, these waves have wavelengths from 30 centimeters to about 12 inches and about 1 millimeter, the thickness of a pencil lead. So if you look at your pencil right now, that pencil lead thickness, that's about how thick a microwave's wave is. This wavelength has enough energy to excite water molecules. So think about if you put water in a microwave and you heat it up, obviously it's going to change from a liquid to a gas, or at least going to boil the water a little bit. And then the friction between the moving water molecules then causes heat in your microwave. Infrared waves is going to be our next one, and this is a region of the spectrum with a wavelength of about 1 millimeter to approximately 700 billionths of a meter. That's a nanometer. And those infrared waves include thermal radiation, which means we can't see it, but we do feel the heat. And the next one is our visible light, which is the one that we can actually see. The rainbow of colors we know as visible light is part of the spectrum with wavelengths between 700 billion and 400 billionths of a meter. So that's 700 to 400 nanometers. And as you can see, there's our little prism, and we have red, orange, yellow, green, blue, indigo, and violet. And I remember this how? Roy G. Biv. Here is another picture of our prism and our light spectrum. Just to put that out there. We have ultraviolet waves is next, and ultraviolet radiation has a range of wavelengths from 400 billionths of a meter to about 10 billionths of a meter. Sunlight contains ultraviolet waves that can burn your skin. So yes, UV rays, that is going to be what you're getting outside in the sun and while we're wearing sunscreen to protect ourselves. It's also the type of waves that are created in tanning beds to try to get you tan, which don't do that, protect your skin. X-rays. So this is our next one, and these are high energy waves which have great penetrating power and are used extensively in medical applications for inspecting metal welds. Their wavelengths range from about 10 billionths of a meter to about 10 trillionths of a meter. Last but not least, we have gamma rays. And gamma rays are going to be the wavelengths that are less than about 10 trillionths of a meter. These gamma rays are generated by radioactive atoms, which we talked about in our radioactivity unit if you do want to go back and look at that. Gamma rays have even higher energy than X-rays, and the energy is so high that it can push electrons right out of the atom and even break chemical bonds, which we talked about last unit, including the chemical bonds holding molecules together in your body, which is why it's very dangerous to us. Color. Each wavelength and frequency of light has its own color. So if you look below, red is 650 wavelengths, orange 600, yellow 580, green 530, blue is 470. And notice how the frequency goes up as the wavelength goes down. Color wheel of light. When light is emitted by an object like your TV, the colors overlap with each other. And that is considered, remember, our constructive and destructive interference in part 2. This is our constructive and destructive. And we could divide up the light into a fundamental color. And we would have 3 primary colors, which is our red, blue, and green, which I'm sure you've talked about in art before if you've taken art. When these colors overlap, we can see how they combine and make more colors. It can also be called additive color wheel. So our secondary color, we have magenta, yellow, and cyan, which is like a type of blue. And then our tertiary colors is going to be white when all of the colors overlap, like a piece of paper. A color wheel for pigments are anything that light will bounce off of, like paint, crayons, and ink. When the white light hits a pigment, some of the light is absorbed and others of the light are bounced back. Remember, what bounces back is what we are seeing. It can also be called subtractive color wheel, which is, here's another example. Here is a color wheel, and it just kind of has like the degrees, and it just kind of shows you some things that are in this area or category. And then just another example of our electromagnetic spectrum. So I hope this, guys, helps you out a little bit. And if you have not done your foldable, use these to help you because that's what I'm here for. And then if you have not done your Waves Town, make sure you do so. Have a great day, guys.